I guess you can start. Go ahead, thanks.
Okay. All right. Hello, everyone. My name is Yu Hui. I'm currently a CS PhD student at Stanford University. Today, I'm going to present pre-trained language models do not help auto-regressive text-to-image generation. This is a joint work with Brandon, Zhe, Waishao, Alex, when I was interning at Apple Machine Learning Research. So text-to-image generation aims to produce an image given a text description. There are two current paradigms for text-to-image generation: diffusion-based and autoregressive-based. Autoregressive-based text-to-image generation is enabled by the image tokenization using VQ-VAE or VQ-GAN. Given an image, the image tokenizer transforms it to a grid of discrete tokens. And with these discrete tokens, we can reconstruct the original image. Here is a real example using state-of-the-art VQ-GAN. As you can see, these image tokens preserve most of the information of the images, as the reconstruction is nearly perfect. With these discrete image tokens, we can do the joint modeling of image and text tokens in autoregressive fashion. Here, take a language model, we modify their embedding layer and output layer so it can take both image and text tokens as input and output. And this framework has a lot of advantages. First, this is a very simple framework, and it unified both image understanding and image generation. And it could enable many capabilities, such as the in-context learning and image editing, like language models. And the autoregressive-based methods and diffusion-based methods achieve very similar performance in text-to-image generation. Here, the blue points shows the autoregressive methods, while all the gray points shows the diffusion-based methods. What is interesting here is that all the diffusion-based methods use pre-trained LLMs as their text encoder. And they found that the pre-trained text encoder significantly enhances the image generation quality. One notable work is Imagine, where they show that using stronger text encoder is much more useful than scaling up the UNet in diffusion models. However, all the autoregressive based methods, none of them use pre-trained LLMs, and they are all trained from scratch. So here, our question is, can we improve the autoregressive-based image generation with recent advances in pre-trained LLMs? And surprisingly, we found that the pre-trained language models do not help autoregressive text-to-image generation. Here is our main result. We show the loss during the training over 100 billion tokens. And the red line represents the model start with pre-trained language models. And the blue line represents the models start with randomly initialized language model. As you can see, through the entire course of training, these two curves are almost the same. And at the end of the training, both models can generate high-quality, realistic images. And they achieve nearly the same FID score on the COCO dataset. We further break down the loss on the image and text tokens. And we found that using pre-trained model or random model achieve the same loss on the image tokens. As for the text token, while using pre-trained language model helps at the beginning, but soon this advantage disappear as the training proceeds. And we observe a catastrophic forgetting of text capability after the training. We found that the knowledge and in-context learning capability of language model get lost. So why does this happen? We hypothesize that the image tokens are very different from text tokens, so that a model trained on the text tokens can't transfer to these image tokens. To verify that, we do the unconditional image generation experiment. We train the model only on the image tokens without any text token. And here, if the image tokens share some semantic similarity with text tokens, we should expect the lower loss on these image tokens. And our results demonstrate that using pre-trained and random initialized model just gets the same performance on these image tokens. And if you freeze the weights of the pre-trained language models, the results get worse. So what does this imply? It means that the optimal for the image tokens are drastically different from the optimal for the text tokens. If you start with pre-trained LM or random initialized LM, they reach the same optimal, but this optimal is far from very different from the optimal for text tokens. And if you restrict the model capability by limiting the tunable parameters, it fails to reach this optimal and get worse performance. So why these image tokens are so different from text tokens? Our hypothesis is that maybe the image tokens doesn't have any semantic compared to text tokens. To validate this, we perform the image text token contrastive alignment experiments. And our results show that for each image token, there is no semantic meaning aligned to that. So this raises a very interesting future question. So for image tokenization, what are good image tokens? To answer this question, let's first think about the cross-lingual transfer phenomenon in NLP. So many works have found that if you train a model on a source language like English, it can transfer to other languages. And the more similar of the source and target language, the higher transferability it is. Now let's think about the cross-modal transfer in our case. So we are interested in taking a pre-trained language models transfer to the image tokens. We show that the WQGAN tokens have no semantic meaning, so there is no similarity between the image tokens and the natural language, making the model not transferable. What could be some transferable image token representations? One extreme is about image caption. So if you take the image caption as the image representation, you don't need to fine-tune any LM, and it will understand what you are describing about a given image. But the problem is that the caption lost some information of the original image. So suppose I give you a description of a cat image. You can't reconstruct the exact same cat image as I have in my mind. So will there be some intermediate image token representation that both have semantic meaning as the text tokens, while they return the information as the original WQGAN tokens? Some recent works show promising paradigm. For example, they try to align the WQGAN image tokens with the text and with some regions. And hopefully, these image tokens can make the language model better consume these tokens and understand these tokens. However, this is still an active research area, and there is no definitive answer yet. So thank you for listening. If you are interested, please check out our papers for details.
Fantastic. Thank you so much. Please go ahead. Yeah.
Hi, thanks for the insightful talk. I am unable to connect the findings from this work with the findings from other line of work, and one of which was presented in the session today, which says that, pre-trained language models and pre-trained image models are aligned with each other. So do you have any insights on like how the findings here are different from, is it because we are using VQ-GAN tokens, not like clip embeddings? That's the main difference?
That's a great question. So I haven't been here for another image text alignment, but if you so based on what you described, they are using continuous image tokens. Maybe this is one major difference, as here we are using discrete VQ-GAN tokens.
Right. So actually, can I ask?
Yeah, sure.
So when we use discrete VQ-GAN tokens, so those are just discrete numbers. But I imagine each number is associated with a vector representation coming from VQ-GAN, right? So when you say that, they are not aligned or, so is it based on the discrete number representation or the continuous vector representation corresponding to each code in the VQ-GAN codebook?
Yes, we have tried both. So first we take this image token, discrete token, directly to the LLM and found they can't understand. And then we take the image representation and the text representation doing contrastive alignment and found that after contrastive learning, each image token still can't find the meaningful interpretation of these image tokens.
I see. That's interesting. So I guess my last question would be, how does that relate to, like in CLIP, we know that, for each image patch, you get a vector representation. And we know that that is usually aligned. It has some semantic meaning when you connect it with language. So what is the difference between that and the VQ-GAN tokens?
Yeah, that's a really good question. So I think if you're training a VLM in a continuous representation, usually there will be an end-to-end learning process. But for the VQ-GAN token learning process, it's purely based on the image reconstruction loss. There is no text objective in this pre-training process, and that might explain like why you use continuous token, the results are different, because there is a text objective trained in an end-to-end fashion, whereas VQ-GAN token are not training objective doesn't include any text objective.
Okay, thank you.
Yes, thanks for the great questions.
Thank you. Any other question? No? Buddy? Well, I actually have a follow-up to the question, basically. So when you had your, I don't know if you can go back to the image where you show the actual model architecture that you used. Yeah. Yeah, so this one. So somehow, again, similar in spirit regarding the nature of the input there. So are those newly initialized embeddings that you're adding to your language model, or you're still using the original tokenizer to tokenize them and then feeding them through your language model?
Yeah, that's a really great question. So you are asking like when you're adding this new image token vocabulary, how we initialize this image token embeddings. We have tried 3 different methods. The first method is just random initialization. And the second method is using a mean embedding of the word tokens, because some recent works show that this will be the best when you're adding a new token to the vocabulary. And thirdly, we use the contrastive aligned representation for initialization, but all of them lead to the same results.
Right. Okay. Yeah, because I was mostly wondering whether there is a distinctive difference between the embedding spaces and that somehow has an impact in the training regime overall. Yeah. Okay. Thanks.
Okay, thanks.
We're almost at the end of the session, so I don't know if you're interested in one final question. Otherwise, I'm happy to close the session here. This was our last paper. So yeah, please, let's thank the speaker. Thank you so much.